Thanks everyone. So it's yeah, it's not to comment. Chocolate introduces AI for ads. So much like all of AI, a lot of the ideas behind this work came about in the 1970s, and we're just rediscovering them now. So it's a really nice example of everything that's old is new again. So what I'm going to talk about today at its core is really how do you do an online and distributed mathematical optimization in a real-time environment. And of course, I'll use the display advertising setting as a way to demonstrate this. So before I move any further, I definitely want to call out the various collaborators that we have at Amazon, spanning both research and engineering across multiple locations on Earth. So it's not just here in Seattle. And otherwise, if you're interested in the gory details, there's 2 references there that you can check out. We'll check them later up. So, of course, I'm from Amazon, so we're really big on Flywheel. The Flywheel, it's one of our favorite things. So typically, there's a Flywheel for the retail business about how various activities reinforce growth in the company. And we have our own version of that over in the advertising space. And in particular, this Flywheel has 2 major components. One of which is programmatic optimization. That's what I'm going to talk about mostly tonight. And that's, of course, these algorithms to make real-time decisions and stuff like that. And of course, these such algorithms have to also work in partnership with manual optimization, so the activities and decisions made by actual human campaign managers and other agents. Another idea is to get all of them to work together in harmony. So, display advertising, what's it about? And why is there going to be so much maths involved? Well, effectively, what kind of problem are we trying to solve? Somebody visits a website, and and of course, there's many such events happening in real time, and we have to make very quick decisions within tens of milliseconds as to which ad to show you. And of course, we have in practice hundreds or thousands of machines that make these kinds of decisions in a split second. And so what you have here is, and I'm walking through it, is it's a very large scale real-time optimization problem. It has elements of learning. It has elements of non-stochasticity, so non-randomness. I'd argue that perhaps behind high-frequency trading is possibly the second most large-scale and lucrative application of machine learning in industry today. So just to familiarize everyone with the setting. So the idea is that some person, that individual on the left there is actually one of our campaign managers. So say she is a market for boots, but did not get by. May have visited various sites, Zappos, your favorite shoe vendor online. And so, of course, that person might go about their day then visiting other websites or perhaps other mobile apps. And at some point, they land on a website where there's an opportunity to show an ad, whether there is unsold inventory. Now, unbeknownst to most of you, unless you work in advertising, there's a complex set of decisions that take place in the space of fractions of a second in the form of real-time auctions. And so what that means is that Washington Post here is going to send out requests to a whole bunch of bidders, which ad you want to show. You've got 10 milliseconds. And so that auction, of course, goes to multiple bidders. And like any auction, well, you know something about what you're buying. There's an example of an auction where you're painting, and you painted it, time period, what it's about, and all that good stuff. And so we have a similar decision to make. Given this information in real time, we have to decide, okay, well, among the possibly thousands of ads we can show you, which one should we show? And so come back to the example, there's that real-time auction, and there's multiple bidders. So we're not the only bidder in this game that's being played here. There may be multiple other exchanges or demand-side platforms that are also vying to show you that ad in that moment. Now, ultimately, what this is all for? Well, what are the goals in advertising? Why is there such a business? Well, fundamentally, it boils down to the fact that advertisers have goals, they have objectives that they like to meet. That's why they come to Amazon. So among those goals, one of the most common ones that everyone's familiar with here is clicks. But one of the things that we actually do have quite a bit of power to deliver to the advertiser is additional types of user activity as goals. So what if Mr. Advertiser, you want to drive what we call considerations, so visits to a detail page on Amazon. Maybe you want to drive mobile downloads or purchases on Amazon.com. Or perhaps conversions. You want to get people to sign up for a credit card, sign up for a new phone contract, that kind of stuff. And of course, as Amazon, we have one distinct advantage in this space, which is we know what we buy better than anyone else does. So that's a very, very attractive value prop for the advertiser. And ultimately, the kinds of things that we're beholden to, however, is of course we want to do a good job at being able to drive up conversions. Okay, so what we call response rates, so the rate at which people are going to buy or purchase or download apps or whatnot. And we want to do this within some reasonable costs, in particular within the budget of the advertiser. Okay. So I'm not going to say too much about the other parts of the advertising business where Amazon also plays the role of a publisher and other intermediaries, but that's talking for another time sometime. So coming to the problem of ad allocation, so this decision of which ad should we show you, what are the kinds of things we should consider? Well, we should consider the user, the web page, and ultimately, the output of any algorithm we're going to come up with is going to be which ad should we show, and how much are we willing to pay to show you that ad once. Okay. And the complicating factor, and the reason why this is a 30-minute talk and not a 5-minute talk, is that we have advertiser constraints. Okay, so advertisers often have these annoying things like deliver my budget, deliver 100% of my budget by the end of flight time, or stick to this, get me a cost per action below some value. We'll give you examples of this. These actually turn out to be hard, even from a theoretical point of view, if you're interested in online learning and optimization. And just to tack on top of this, the kinds of additional challenges we face in practice are, well, in terms of scale, we're dealing with billions of requests per day, so that's a couple of 100,000 opportunities to show ads per second, okay, on a global scale. So every time somebody visits a web page, someone will open something to add to it, that's an opportunity to show an ad. Have these annoying constraints and objectives, of which there can be multiple competing ones, but down to arbitrary. We have to do all of this, very quickly, within a few milliseconds, in online fashion. So this is an online learning point, which means there's no concept of going back into the past and changing your mind about which ad you show something that's and last but not least, we have to do this across hundreds or thousands of machines and with communication. So definitely not your textbook machine learning problem that fits in a single post. Now, I'd be lying to you if I said that we were the first people on Earth to think about this problem and come up with a solution. And sure enough, there's a good amount of work that's come out of the various teams at Google, Facebook, Yahoo, back in the day, research. And we have this to break up into two broad classes. The first are, well, I'll call approximation algorithms, right? So you basically, effectively, you show that my allocation is a really hard problem, so we're screwed, so let's approximate the solution using this thing, and that gets you your paper somewhere. Second class of methods are, we're considered more heuristic, but they tend to work reasonably well, more control-based methods. So treat the problem of trying to satisfy constraints as a control type problem. Okay, so here's how that well. Of course, they both methods have their advantages. It's nice to have guarantees in adversarial settings, and I'll say a little bit more about that in a little bit. Control-based methods happen to be simple to implement, so we want to be able to capture both of these and also be able to have an honest discussion about distributed aspects, which has been discussed in some of this paper, to my great surprise. And second, we like a method that actually can generalize the number of ad allocation problems for advertising. So rather than reinvent 17 different algorithms, just have one algorithm for all different problems. One before I continue, I just want to make a distinction here between prediction versus control, because these often get confused, not just in the ad space, but in machine learning in general. So it's worth just spending a little bit of time on it. So in prediction, you're interested, it's typically, your possible modeling problem, right? So predict what the user is going to do, measure that. So, estimating click-through rates, or predict whether or not the user is going to vote so that's one thing. That's different, however, from control, which is actually decision making. So using some predictions in order to make decisions that affect your person or the environment or something like that. And typically, in the course of performing control, you're trying to maximize some objectives, presumably business objectives. So I just want to emphasize that what I'm talking about here is really a control problem, not so much a prediction problem. I'm not too much about that first bit. Okay. So how are we going to think about this? Well, pretty much from its inception, from the very first ad server that was fired up back in the late 90s or something like that, ad allocation is fundamentally an optimal matching problem. Okay, so what that means is we're trying to match, on the one hand, opportunities to show ads to ads that we have. And we want to do this in such a way that we maximize the total value that we generate from doing this matching. Okay. So if you prefer, or for some other analogies, if you are Uber, the left-hand side corresponds to taxis, right-hand side corresponds to producers. If you're Airbnb, left-hand side corresponds to residences, right-hand side corresponds to Airbnb users. If you're a national organ donation agency, left-hand side will be donors, right-hand side will be recipients. Okay, so there's lots of examples of this kind of problem in applied science and industry. So what we're going to do is, okay, we're going to try to match in the ad setting, give requests opportunities to show ads with ads. And imagine that, on the left side, there's, an enormous number of these, billions per day, right? And not only that, but they come to us sequentially, so that you don't get to see all of them in this nice little fashion. You have to make a decision on the fly. And otherwise, we have to do this given knowledge of, well, just how effectively, how much do we gain from matching a particular ad to a bid request, so the IJ pair presentation. Subject to the constraint that I can only show out one ad per bid request, and subject to these annoying long-term constraints, which are really going to make things hard for us. Okay. So the way we're going to think about this problem is to introduce what we're going to call assignment variables. Those are x's. They're just binary. Okay? They're 0 or 1. They're 1 if I show an ad for a bid request, and 0 otherwise. So algebraically, the matching problem can be formulated as a linear program, or LP for short. Okay, where the goal is to maximize the total sum over all of the edges ij. Right? So each one of these ij's corresponds to a blue line. And I want to do this in such a way that the total sum over weights is maximized. And of course, I have a constraint that I can show at most one ad per bid request, and otherwise I have non-negative sections. And this term here that I circled, that's going to be our, effectively, our utility, if you like, of assigning an ad for bid request. It's just our valuation, Bij, minus the price that we're going to pay for that bid request. So just very quickly, I lied a little bit. I said I was going to talk about prediction. I'm just going to briefly mention predictions here, right? Because it comes up a lot. So typically, in the background, we have a model, a probability model that is able to produce this probability estimate, the probability that a user for a bid request I is going to convert eventually a given ad. And typically, we use this probability to derive a valuation, which is just expected value. Right, so expected value for a new random variable is just a probability and some non-zero times. That's convenient, easy to compute. And otherwise, that non-zero amount tends to be specified by the advertiser for our purposes. Okay, so there's an algorithm that solved that problem that I just demonstrated exactly and fairly cheaply. So for each bid request, we can do this in completely online fashion. For each bid request, take all your candidate ads, rank them by this valuations, this expected value, and select the ad with the highest value. Okay, set your bid, put them quotes, to be equal to this value. If that bid happens to be larger or equal to some concept of winning price, I can say anything about what the winning price comes from, then congratulations, you get to show the ad. Hence, I set Xij star to 1 and 0. Otherwise, too bad we lost, nothing happens, all the executives. Very simple. This is just ranking at the end of the day. Just pick the ad with the largest D. Let's do this completely online. This is great because you can parallelize this across thousands of machines, and you can run completely online project. It's beautiful. Engineers love this. And life would be really that simple in advertising, and that'd be done now, except that those are million constraints, which I'll get to in a moment. Before I get to that, here, just to establish some notation that vectors are going to be useful to us. So I'm going to slice up the time axis into, into actual intervals of walk-on time. Think of each of these boxes as 10 seconds of time, something like that. And within, any slice of 10 seconds, there's a number of bid requests that we process and decisions that we have to make. And in the process of doing this, of course, we get some utility out of it. And in the process, we also get some constraints. Okay? So I'm going to think of the constraints here in terms of matrix vector products. Okay? If it helps, think of what I call matrix AT there as the amount of money I'm going to charge advertiser J if I serve their ad once. Right? So this is the kind of notation for the exact same problem, vector notation that I use. And now, those are my non constraints. So they're everywhere in advertising. They're actually the norm, not the exception. And they take on various forms to as close to as possible to 100%. The budget by the end of flight time, achieve a CPA no more than some target, achieve some viewability, no, but at least this amount. And there's many other examples as well. What makes them hard from an online optimization point of view is that there's time in, as the word says, as a long-term constraint. What you do in the ground is not what matters, it's how you behave over a long time period. I think a long time period here would be 3 months of advertising. So that's really annoying. Just to make this idea really concrete, here's one of those annoying constraints. Slightly more concrete form. So for a given round T, so remember a round here is 10 second slice. So my matrix A might be the matrix whose elements correspond to budget consumed by ads for each bid request. And BT is some vector of target funds, how much I should spend in 10 seconds. And I'm just going to define AX minus B as just a vector of errors in budget consumption for 10 seconds. Okay, so the reason I introduced through that vector notation in there is it allows us to simplify notations at some levels. So we're going to model this as an online convex optimization problem. Okay, so what does that mean? It means that we're going to break up the time into a bunch of rounds, and each round is a 10-second period. And the game goes something like this. The player, that's us, we play a vector entity. Okay? That vector corresponds to the 0, 1 variables I described. The external world is going to respond with the reward U, and that's the vector utility that we get, right, from serving ads for 10 seconds. And a constraint violation in X minus B. Okay, so that's the allocation vector, that's the performance, and then your budget and target, so that's your error. And then we want to make decisions in such a way that over T round, which is a large number, we keep this error in constraint valuation small, right? So you don't want to overspend, you don't want to underspend. And otherwise, you want to maximize utility you get by exercise. That's the online convex optimization problem we're going to solve. Now, some of you may be thinking, well, who generates these A's or these U's or whatever? And the answer to that is equal wizards. No, but more seriously, what I mean by that is we don't actually make any assumptions about how the A's or B's or U's or various concepts are generated. In fact, they can be generated by the most evil, powerful beings in existence. And still in that environment, the goal is to come up with algorithms that do well in that kind of environment. Now, why would we do this to ourselves? Great question. I'm glad you asked. Well, because the kind of environment that we operate in display advertising is ever changing, and there's a whole bunch of aspects to it that really make life quite difficult. So I mentioned this idea of going to bid, to win in production flow. You don't know what kind of options is being run. Developing ad serving code, introduce production new features. I mentioned these lovely campaign managers who are also doing things on the side. Well, that's all nice and good. It's part of business. At the same time, it's sometimes there's no governing model around that. So hardware failure to get that, right? So take all this together. Good old Black Friday, right? We love Black Friday. So take all this together, and you have the makings of a truly adversarial environment. So you want algorithms that do well in this environment. Okay. Right. So here's the algebraic form of the problem. Okay, so just as I said, we want to maximize utility and we want to penalize deviations in strings. Okay, and at first, that function e. So we introduce a function e here that's nonlinear and concave in particular. The introduction of a nonlinearity seems to break that really nice ranking algorithm that I suggested earlier. But thankfully, a little bit of convex analysis shows that this is so. So what that means is, let's look at what's called the ranging function. So take function out of -4 and introduce a what's called a potential dual function, that funny E star at the end. And the first thing you'll notice is, this function here remains linear in the x's. That's great. That's beautiful. It means I can keep on ranking. Except with modified types, I'm going to rank with not just based on U, but also based on these dual variables and my A's. And so I introduce these dual variables that help me penalize deviations from strings. So the algorithm ends up being fairly simple at the end of the day. So again, we proceed in rounds. On the one hand, we're going to make decisions, okay, given a set of dual variables. That's what we call ranking and bidding. And then, effectively, what we're going to do is we're going to look at that gradient term is basically telling you what kind of mistakes did I make in the last 10 seconds. Okay, that's what that gradient is telling you. Gradients are like errors, right? That's more or less the way they're introduced in college. And so, okay, what mistakes did I make? And that's captured by that gradient. And now I'm going to take a step, actual variables and update. And I just keep on doing this over time. The way this translates into a more applied setting is, so you might have on the orange rectangle here, you've got hundreds of machines making decisions in real time, okay? And they're just using the latest numbers that they've got, right? Every 10 seconds or so, they're sending all of their information back to the navigation feed that's basically just counting how much budget have they spent for this app. Okay, that's the little blue boxes there. And otherwise, we're adjusting our dual variables, our lambdas, based on the error that we're making. It's very much like an integral controller. Okay. And just do this in totally online fashion. And it works great. So, very quickly, so a couple of things that we looked at here in terms of results. So here's a simulation that we did with 36 ads, comparing our mapping from blue to, so green shows a proportional control heuristic, and red shows a kind of dual averaging scheme, both are around there. And so what you want in each one of the panels here is for the curve to compute to the 45-degree line. That basically says that you're able to stick to a particular fluid profile that we specified. And so red method tends to have a bit more variability than any of the other methods. And otherwise, in terms of the way it works in advertising is, you either get really good accuracy in how much budget you consume or how much performance you drive, you can't get both all the time. And so ultimately, this plot here shows that there's going to be trade-offs in doing this. So where you get very high performance, for example, you may have to give up on the constraint, potentially. Not surprising. Some other results. So here's another smaller scale test that we did online. So this is our actual ad serving machine with 7 ads. So this is a proper A/B test. And here we're looking at, on the y-axis, return on ad spend, so ROAS. That's the Amazonian measure of advertising performance. Basically, how much money did we put into the advertisers' pockets from advertising with us, because they sold lots of units of X, versus how much they spent with us. Okay? So you want this, you want to come on the left with the positive, and then in terms of delivery, you basically want all of these bars to be close to 100%. So that basically says that you're delivering on schedule, and so that's called on schedule here on the side. Okay. Yeah, so the large scale test that we did with large advertising pools, basically the exact same idea there. Just in the interest of time, let's go to this one here. So basically here we had, we looked at ads that were previously under-delivering or over-delivering, so either of those are good. Right? So we basically want now to increase both of those towards positive 0. So I'm sure that we see that here. And similar story for performance, you want less ads that underperform or overperform. Right, more ads to that. That's actually all I had. So I'll talk to you about that.
All right, thanks so much. Great talk. I'd love to open up the floor again for another question and answer session for about 5 minutes or so. So if you have a question, please raise your hand and we're going to have a microphone run over to you. Thanks.
Hi, thank you for the excellent talk. So I just have one quick question, maybe a more complicated question after. So the first one is, did you have a problem with your gradient vanishing? Because you took the gradient of the Lagrangian, and by like page 18, you did the Lagrangian, the gradient to 0.
So remember, we're not at the optimum, and this is an online environment, right? So in general, actually, that's what we want, but it's usually not what we get.
And this second one is, actually maybe this is easier. So you gave the linear programming relaxation of the Boolean assignment, but I was wondering how you go from the optimal x values to actually assigning, because you can't actually, do you take like the R max or something?
Yeah, so a couple of things. One is that the relaxation in this case is exact, because the adjacency matrix of your graph that you're matching on is submodular. It's TUM, right? So it's actually exact. Second of all, it's also the case that the only thing you need to do to compute solutions to that problem is the R max operation.
Okay. Yeah.
That's all. Yeah. It's all improved. Ad nauseam.
Could you define overachiever? Is that because it had too much click through, and so you couldn't sell another one? What's your definition of an overachiever?
An overachiever. Not sure what your.
I bet you were saying over.
Oh, so sorry. Yeah, I went through this slide a bit too carefully. I meant underperforming versus performing on par with expectations.
Did you have over?
I had over-delivering. Yeah, that's.
And why is that bad?
Yeah, so over-delivering basically. So imagine that you're the advertiser. You gave me $10,000 for your campaign. I come back, hey, surprise! I spent $30,000.
No, it's not quality of the ad.
It's the amount of budget that we consume as a platform. That's right. But the converse of that problem is also bad. So again, you asked us to spend $10,000 on an ad campaign. We come back, hey, we spent only half of that. Actually, they also get mad at us for that as well. on the grounds of, insufficient reach and,
So it has zero to do with conversion rate.
indirectly. Somewhat to do with conversion rates.
Well,
Okay, so I'm not too familiar with the primal dual method, but I saw it at a talk given the summer at the Data Science Summit by Professor Michael Jordan, and he was talking about using it for doing gradient descent and accelerating it. I was just wondering if you knew of other good uses of primal dual method, other than for the optimization purposes, removing that sort of nasty nonlinearity in your constraint optimization that you were talking about.
Yeah. Primal dual methods are actually very, very general. So those of you who are playing around with deep learning, you could technically solve deep learning using the primal dual method. There's also lots of good reasons why you wouldn't want to do that, but you could in theory. It's a very general way of doing optimization. It happens to be particularly convenient here in the way it allows us to separate a problem into these nice little clean, simple pieces. But there's also lots of other examples where, like if you have a problem where it was hard to deal with constraints in primal, then you can try solving the dual method and put that to work. There's lots of applications for these kinds of methods beyond this. I mean, if you're asking like a technical application areas, I mean, just recommendations when it comes to time.
Any other questions? All right, well, that's our Q&A session. Thanks for coming out, everyone. Let's give Dr. Jim Huang another hand.